Welcome to The Explainer. Today, we're diving into a completely fascinating, almost detective-like investigation into the very foundation of artificial intelligence. You know, we talk all the time about the story of AI evolution and how incredibly fast software is moving, but we rarely stop to talk about the physical constraints that are holding it back. Well, today, we are looking at how AI is stepping up to unblock hardware engineering itself, specifically through a groundbreaking new architecture from NVIDIA called Nemotron 3 Ultra. It's a pretty wild paradox, right? Think about it. The big question we really have to ask ourselves is what happens when the hardware running our AI takes way too long to build? Right now, modern chip design is severely limited by human engineering time. We're essentially waiting around on human minds to meticulously map out the physical pathways that our future AIs are going to run on. And as these AI models get exponentially larger, the hardware required to run them gets exponentially more complex. Okay, let's dive into this. If we're going to understand this bottleneck, we have to understand the language of chips. We're talking about register transfer level code, or RTL. Now, this isn't your standard software programming. RTL dictates the precise microsecond by microsecond temporal behavior of hardware chips. It requires some highly specialized knowledge just to write, and even more to actually verify. When an engineer makes a mistake in RTL, finding that bug during tool-based validation is literally like finding a needle in a haystack. The correctness of the entire chip absolutely depends on this exact precision. Section 1. The chip design bottleneck and why hardware desperately needs a detective. So the reality of writing this RTL code, it's incredibly iterative. You're not just typing in a prompt and calling it a day. It's complex, iterative detective work. Engineers have to generate the code, run it through compilers and simulators, inspect the waveforms, reflect on the verification feedback, and then try to fix it. Complex RTL tasks are almost never solved on the first try. Honestly, it's a grueling cycle of trial and error. Moving right along to Section 2, enter the ACE-RTL agent, an iterative investigation. Let's actually break down how this tech detective works. It's built specifically for this iterative workflow and has three relentless components. First up, the generator, which produces or updates the RTL code. Second, the reflector. This analyzes the simulation feedback, essentially looking at the clues from a failure to find the root cause and propose a fix. But the third step, this is where the magic happens, the coordinator. The coordinator maintains a running debugging context across all these iterations. It decides which history and feedback should guide the next attempt. Because of the coordinator, the AI doesn't just blindly guess. It builds on previous failures so it never makes the exact same mistake twice. Which brings us to Section 3, the brains, Nemotron 3 Ultra. Powering the investigation. All right, let's look under the hood. Nemotron 3 Ultra is a massive 550 billion total parameter model with 55 billion active parameters. And it uses a really fascinating mixture of experts' hybrid Mamba-Attention architecture. Why does that matter to us? Well, in RTL workflows, the context gets absolutely huge. A single debugging iteration includes the specs, the module code, simulator outputs, assertion failures, and literally all prior fix attempts. This hybrid Mamba-Attention design drastically reduces attention cost and memory footprint. That allows for a massive 1 million token context length while delivering up to 5 times higher throughput. It is perfectly designed for long-running, complex memory loads. And this brilliantly illustrates exactly what that architecture achieves. Look at the pass rate on the CVDP benchmark for debugging realistic hardware problems. When paired with the ACE-RTL agent, GLM 5.2 hits a solid 94.3%, and Kimi K2.6 hits 97.1%. But Nemotron 3 Ultra, it achieves a flawless 100% pass rate. It perfectly isolates and fixes the bugs in these complex tests. But hey, accuracy is really only half the story here. Across 9 different CVDP task categories, Nemotron averages a 97.1% pass rate, which edges out Kimi K2.6. But look closely at the token usage. This is a massive contrast. Nemotron uses only about 6,600 tokens per iteration on average. Kimi, over 22,000. That means Nemotron 3 Ultra is delivering higher accuracy while using 71% fewer tokens. So what does this all mean for us? It basically boils down to this. A higher pass rate means the agent solves more unique hardware problems, while lower token usage reduces inference overhead for every single refinement step. This doing more with less angle, it's literally the holy grail for practical AI coding. It means engineering teams can tackle far more tasks and run far more iterations, completely within their existing compute budgets. Moving to Section 4, training for real-world hardware, the synthetic data generation pipeline.
So the crucial point is how they actually taught this model. Traditional models, they're just trained to write clean code from a prompt. But Nemotron 3 Ultra wasn't just trained to write, it was trained to be a detective. Sure, it does spec to RTL, generating code from scratch, but it was also trained heavily on editing, modifying existing implementations for weird corner cases. And most importantly, it learned debugging. They actively injected realistic hardware errors, things like timing violations, into the training data. The model had to learn to repair faulty RTL using diagnostic info. It was actively trained to fix broken things.
And they didn't just throw all the synthetic data at the model blindly either. Actually, scratch that. They were extremely meticulous. Every single training sample was rigorously filtered using an LLM as judge to ensure structural validity and semantic alignment. This basically guarantees that Nemotron only learned from the highest quality, most realistic hardware examples out there. Section 5, Building Chips with AI Today, Real-World Integrations. The real-world impact happening right now is just staggering. Major engineering teams are already deploying this. Cadence is integrating Nemotron 3 Ultra into its chip stack AI superagent to orchestrate the entire debugging process. Siemens is pairing it with their Questa 1 toolkit for massively improved token efficiency. And Synopsys, their agent engineer, is using this tech to achieve autonomous verification closure. They are quite literally turning what used to be weeks of grueling manual verification effort into mere hours. Which brings us to a final, pretty wild thought. If AI agents, powered by incredibly efficient models like Nemotron 3 Ultra, can autonomously orchestrate, debug, and verify the physical chips that will power the next generation of computing, what will human hardware engineers invent with all their newly freed time? When we finally remove this massive bottleneck of manual verification, the pace of hardware innovation is going to absolutely skyrocket. I, for one, cannot wait to see what they build next. Thanks for joining me on this explainer, and definitely keep your eyes on the future of hardware.